One specific corollary to the mean value theorem for derivatives that you might see on the AP is something called Rolle's theorem. Now, Rolle's theorem is just one specific example of the mean value theorem for derivatives. And here's what Rolle's theorem says. It says if f is continuous and it is differentiable, and here's a third part of the if statement for Rolle's theorem. If the outputs of the function at the left endpoint and the right endpoint are the same. That's the difference in the Rolle's theorem. This is the same part of the if statement from the mean value theorem for derivatives, but Rolle's theorem says specifically, and we'll go down here on the graph, specifically your outputs at your left endpoint and right endpoint are the same, meaning that your secant line has a slope of 0. That's what that's going to guarantee. The slope of the secant line will be 0. So Rolle's theorem says that if that is true, then there is at least one value on the open interval, they're still calling it C here, where the slope of the tangent line will also equal 0. So it is the mean value theorem for derivatives, but it's specifically where the slopes, both on the secant line and on the corresponding input values of C, the tangent line has a slope of 0. So instead of calling that the mean value theorem for derivatives, it has its own specific name, Rolle's theorem. So let's move on. Here is another corollary from the mean value theorem called the equal derivative theorem. And here's what it says. It says if f prime equals g prime for all x values in the open interval from a up to b. That's an if. We have to have if before we get then. If those two derivatives are equal for all input values, then there is a constant c such that the outputs on f are going to equal the outputs on g plus that constant c everywhere in the open interval. Well, that's a little bit maybe hard to pick up analytically, so let's do it visually. Let's say that here on the closed interval, we'll say that's A, we'll say that's B. Okay, we're going to look on the open interval. Let's call this f of x. I'll pick up another color. We'll call it g of x, and it can be anywhere in here. But there's one thing that is true about f and g, and that is that the slopes are the same everywhere. I've drawn those such that this is a true statement. For all values on the open interval from a up to b, the slopes everywhere on f are equal to the slopes everywhere on g. There visually is what we're talking about. The then part of the statement, what we get here, is it says that there is some constant c so that the outputs on f are the outputs on g plus c. In other words, this simply says if two functions have the same derivatives, which means slopes, on an open interval, then their outputs, OUT puts, differ by the same constant value on the whole interval. And that could make sense. It doesn't matter where we draw f and g. Everywhere, since they exhibit the same behavior, everywhere on that open interval, it doesn't matter what x value I look at, vertically the difference in the outputs from f and g is going to be that constant value of c, and that's what this is saying. The outputs on f are going to be equal to the outputs on G plus that constant value C. So we know that they exhibit the same behavior everywhere on that open interval.